So at this point, we've added a little more detail to Ernest Rutherford's model of the atom. What we realized is that electrons can have energy levels. Electrons are not just at one distance from the nucleus of an atom, but they're at a variety of distances depending upon the energy that they have. And in particular, the more energy that your atom has, the further from the nucleus its electrons will be found. Now, there's only one slight little incy-wincy problem here, and that is we can only perfectly explain this for the hydrogen atom, which is the simplest atom. It has just one electron. What about for those other 117 elements? What are we going to do there? So this theory continues to develop beyond the Bohr model. So let's kind of take a step back and look at the big picture. We know that electrons reside in what is often referred to as the extranuclear space of an atom. That is, that they are orbiting the nucleus at a significant distance from it. We also know that the more energy that an electron has, the greater distance it will be from the nucleus. And we looked at energy level diagrams like this, and we said that the principal energy level, which we're going to give the symbol N, is a measure of both the energy that the electron has, but also its distance from the nucleus. So as N gets bigger, the distance from the nucleus gets bigger, but also the energy of that electron gets bigger. And N is an example of what is referred to as a quantum number, because it can only have certain specific values. And in this case, the values that it can have are it can be a positive integer. So 1, 2, 3, 4, 5, etc. Now, in the Bohr model of the hydrogen atom, there's only one quantum number required to explain all of the energy levels that we see for hydrogen, all of its emission spectrum. This is the only quantum number. As I mentioned, though, there's a slight difficulty. This simple model with just the one quantum number only works for the hydrogen atom. It doesn't work for the other 117 elements. So this is clearly a problem that needed to be fixed. And the guy that fixed it was a dude called Erwin Schrodinger. And he developed what is now known as the Schrodinger Equation. And this equation has 4 input numbers rather than just the one that Bohr had, and it is able to successfully describe how electrons are organized around the nucleus of all atoms. Now, this is an example of a quantum mechanical model, and what it does is it describes particles as waves. And the other important property about a quantum mechanical model is that it's statistical. So it tells you where things are most likely going to be rather than absolutely where they are. So Schrodinger was very famous for the Schrodinger Cat thought experiment, which explained the statistical nature of quantum mechanics and illustrated some of the limitations. So in the Schrodinger Cat experiment, what you have is a crate that is divided into 2 halves. And on one half you put a cat, and the divider has some air holes in it, so air can move between the 2 halves of your crate. On the other half of the crate that doesn't contain the cat, you have this elaborate contraption. And this contraption has a Geiger counter that, when activated, causes a hammer to fall, and that hammer smashes a bottle of poisonous gas. So it breaks the glass and the gas gets released. And the gas moves over and kills the cat. Now, what determines if the Geiger counter gets activated is a sample of radioactive material. And this radioactive material, it goes off like on average once every hour. Now, sometimes it emits a radioactive particle that can activate the Geiger counter, like, 2 in a row, but then it won't release anything for the next 2 hours. So it really is, a random thing, but on average it goes off once an hour. So if you put your cat in this setup and you nail the lid on the box so you can't see what's going on, and you leave everything for 30 minutes, right, which is half the average time that it takes for the hammer to fall, then how would you describe the cat? Well, statistically, you would say that the cat is half dead and half alive. Now, in reality, we know that a cat can only be dead or alive, but the best that we can do without lifting the lid off the box is to say that the cat is half dead and half alive. So when we're looking at little tiny particles like electrons within atoms, we can't look at them directly because any attempt to do so would cause them to move. So it's kind of like the cat locked in the box. And so what we're going to do is we're going to be using statistics to describe what those electrons are doing. So when we're talking about where electrons are located in space around the nucleus, we're giving the most probable place that they're going to be rather than the exact place they're going to be. Now, if you do this, you can create a theory that works for all 118 atoms on the periodic table. So in the quantum mechanical model that Schrodinger developed, the space where electrons are found about the nucleus is divided in 3 different ways, each with increasing levels of precision. There is what we call the shell, which is exactly the same as the principal energy level in the Bohr model, and that just represents the approximate distance from the nucleus. Then there is this subshell, which tells you where within that shell you are, and that gives you a little more precision. And then finally, there is the orbital that tells you where you are within the subshell. And so each of these is more precise than the next, but we can't get any more precise than the orbital level, right? So it's kind of similar to how like a postal address works. You might say the state that somebody's in, then you'll say the city, and then you'll say the street, right? And each of those things is a little smaller region of space than the other. So we've got 3 qualities here. I said that there are 4 things that Schrodinger had to put into his model. I'll explain the 4th one a little later on. So these 3 things describe where in space the electron is. So electrons in the same shell are at approximately the same distance from the nucleus. This is very similar, like I said, to what we were talking about previously. And you can see the further we get from the nucleus, the bigger the shells get. So it makes sense that as we get to bigger and bigger shells, we can put more electrons in them. So we indicate the electron shell with the letter N, and N will just be a whole number, 1, 2, 3, etc. And then we have a real simple formula that explains the maximum number of electrons that can go into a shell. It is just 2 times N squared. So if I have the 3rd shell, 2 times 3 squared, 3 squared is 9, 2 times 9, that would be 18 electrons, could go into the 3rd layer of electrons. Now, a shell doesn't have to be completely filled up, but if it did get filled up, this shell could contain 18 electrons. Okay, so here it all is spelled out for you. And you'll see in this table it indicates that some of the shells never get completely filled up because we only need up to 118 electrons, right? So the first shell can hold 2 electrons, the 2nd layer of electrons can hold 8 electrons, the 3rd layer of electrons 18, the 4th 32, the 5th 50, the 6th 72, and the 7th 98, and we just calculate that using that little formula there, 2n squared. So you don't need to memorize it. Like I said, shells don't always get completely filled up, and in fact we've never seen an atom that has a completely filled 5th, 6th, or 7th shell. We just don't need it. Think about it. 2 plus 18, 2 plus 8 plus 18 plus 32 plus 50 plus 72 plus 98 is way, way bigger than 118 electrons, which is the number of electrons in our biggest atom. Now, we said that within shells are subshells, and subshells of a given shell have the same energy. So they're different regions of space, but they have the same energy. So they're different regions of space that are at approximately the same distance from the nucleus. So if here's your shell, then maybe subshell A is over here, and then subshell B is over there, right? But they're at the same approximate distance from the nucleus. Now, it turns out that there are 4 different types of subshells. There's S, P, D, and F. And these are indicated with those lowercase letters S, P, D, and F. And these are like getting bigger, right? S is the smallest, F is the biggest. An S subshell can hold 2 electrons. A P subshell can hold up to 6 electrons. A D subshell up to 10. And an F subshell up to 14. They get bigger as we increase across the sequence S, P, D, and F. Okay, so remember that the first shell can only hold 2 electrons. It only has 1 subshell, and that is an S subshell. Now, the subshell notation goes like this. The letter tells you the type of subshell, and then this one is your shell number, right? Okay. When we go to the second shell can hold 8 electrons. It has 2 subshells. It has a P subshell that can hold 6 electrons and an S subshell that can hold 2 electrons. So you put that together, you get your 8 electrons. 2 times 2 squared equals 8. When we go to the third shell, you guessed it, it has 3 subshells, a D, a P, and an S. And you put all of that together, and how many electrons have we got? 18 electrons. 10 plus 6 plus 2, and remember 2 times 3 squared equals 18. When we go to the fourth shell or higher, we get a full set of the 4 subshells. We get an F, a D, a P, and an S. Okay, so we get the whole thing, all right? And that has, what have we got there? 8, 18, 28, 32, right? And 2 times 4 squared gives me my 32. All right, so that's it. Now, beyond shell 5, shell 6, shell 7, we never go beyond 4 subshells, so we don't have to worry about 5 subshells or 6 subshells, etc. Okay, now within each subshell there are orbitals, so we're zooming in even more to get an even finer detail. And an orbital describes the region of space within a given subshell where an electron is, because it's a statistical model most likely to be found. Now, you can only ever put 2 electrons in an orbital, 2 electrons in one orbital. So S subshells that can hold a maximum of 2 electrons, they have 1 orbital. P subshells that can hold a maximum of 6 electrons, you guessed it, 3 orbitals. D subshells that can hold up to 10 electrons, you guessed it, 5 orbitals. And then F subshells that can have up to 14 electrons, and they've got 7 orbitals. So that's how it works. Now, we can't go any finer in detail than the orbital. That's the end of the road. So it's kind of interesting to ask, what do these orbitals look like? You know, what do these regions of space look like? So the orbitals of the different types have different sizes and shapes depending upon the shell and the subshell that they are part of. So a 1s subshell has a s orbital that is quite small, and you see that that is spherical. A 2s subshell is comprised of 1s orbital, but it's bigger because on average the electron is further away from the nucleus when it's in the 2s subshell. And then the 3s subshell is comprised of 1s orbital that's even bigger again. So what we recognize is that s orbitals are spherical in shape, and they increase in size as the shell number increases. So next in the sequence are p orbitals. p orbitals combine to form a p subshell, and there are 3 p orbitals that make up a p subshell. And the p orbitals are quite interesting in shape. They're kind of composed of these 2 lobes that look a little like buns. Sometimes people draw them as 2 teardrops. That kind of tends to be an older style, but you'll still see that out there. And so it is important to realize that in reality they look more like these buns, but people, I don't know why, because by default they tend to draw them like that. So there are 3 p orbitals that make up a p subshell, and these p orbitals are at 90 degrees to one another, directed along the x, y, and z axes respectively. So this is one orbital, this is a second orbital, third orbital, and they're both the same shape. They're all the same shape, all 3 of them, but they're at 90 degrees to each other. They all have the same energy, they're just oriented differently. Now, d orbitals, a d shell is composed of 5 d orbitals, and d orbitals are complicated in shape. Most of them have these 4 lobes, but the dz squared has this cool one where it has like the donut around the middle, which I always kind of like that one. But there are 5 d orbitals that make up a d subshell. An f subshell has 7 orbitals that make it up, and they have even more lobes than p orbitals in each of those orbitals. So they're kind of pretty recognizable. You know, they have like, 6 or even up to 8 lobes in their orbitals, and there's 7 of these combined together make up your f subshell. And these surfaces here represent where it is most likely that an electron will be found. So somewhere on the surface there, normally it's like a 90% probability that they draw it to. There's a 90% probability that you'll find the electron there. Okay, now I said that there were 4 parameters that were needed for the Schrodinger quantum mechanical model. We've only described 3 of them: the shell, the subshell, and the orbital. So what is the 4th parameter that's needed to describe how electrons are organized in atoms? Well, it was recognized through an experiment called the Stern-Gerlach experiment, but you don't need to know about that electrons behave as though they are spinning. And when charged particles spin, it gives them magnetism. They end up with a magnetic field associated with them. Now, it turns out that electrons behave as though they were spinning in either one or of 2 directions. They're either spinning so their magnetic north pole is pointed up, or they're spinning so that their magnetic north pole is pointed down, and never any other way. So the electron spin is also quantized. It can take either one of either 2 values. It's either up or it's down. And we normally indicate an electron spin with like a half-headed arrow pointing either up or down. So this would be called spin up, and that would be called spin down. So this is kind of important because it turns out, this guy called Hund figured this out, that electrons don't join other electrons in the same orbital if there's an unoccupied orbital of the same energy available. So if we're putting 3 electrons into a p subshell, there are 3 orbitals that make up a p subshell, so we put 1 in each of them. What we don't do is pair up in an orbital with multiple electrons and leave any empty, right? Does that make sense? So it's kind of like seats on the bus, right? If you hop on the bus and there's only one other person on the bus and you don't know them, you don't sit next to them, right? Now it makes sense because electrons, they want to keep out of each other's way. They are negatively charged and they're going to repel one another. So if we put electrons into different orbitals, into different regions of space, we're going to maximize the distance between them and minimize the repulsions. Same as why you don't sit next to the big smelly guy on the bus. He's repulsive. You want to put as much distance from him as possible. Now, there's also another rule, and this was identified by a guy called Wolfgang Pauli, and he was really obsessed with how things are spinning, and this is him. This is Wolfgang Pauli here, and I think this is Niels Bohr when he was older, and they're looking at a spinning top because Wolfgang Pauli loved thinking about how things spin. And he says that no more than 2 electrons can occupy the same orbital, and if you do have 2 electrons in the same orbital, they have opposite spins. So here I've got an s subshell that I'm going to put 2 electrons in. And so the electrons go in with opposite spins. They don't go in with the same spin, right? You never put 2 electrons with the same spin into an orbital. Here I've got a p subshell composed of 3 orbitals, and I want to put 4 electrons in it. So I have to make sure that I'm in agreement with both the Hund's rule and the Pauli exclusion principle. So Hund's rule says don't pair up electrons in an orbital if there's another orbital available to put them in. So this electron needs to be over here because it's got, I've got an empty space there. Now I have to think about Pauli's exclusion principle that says if I do have 2 electrons in an orbital, make sure that their spins are opposite. So this is no good. I got to flip the spin, right? And now I have a correct electron configuration, right? 4 electrons in the p subshell will always go into the 3 orbitals that make up that subshell in that way. Okay, so let's have a look at some ALEX problems regarding recognizing s and p orbitals. Now, there's this nice little diagram that I found that shows the general shapes of all of the orbitals that make up the different subshells. So this is an s subshell. It's made of 1 s orbital, and the s orbitals are kind of spherical. This is a p subshell. It's made up of 3 p orbitals at 90 degrees to each other. They all have this shape where it looks like 2 buns resting near one another. This is a d subshell. And we have the 5 different quite complex orbitals that make up the d subshell. And then finally we have an f subshell with the 7 orbitals that make up the f subshell. So are any of these guys an s orbital? And I think the only one that could be would be a. So that one is that one. So the answer is yes. List the s orbital, if any. It's got to be a. All right. Are any of them p orbitals? So this guy is like nothing, and this guy is nothing. Now don't get confused. You might think that this is like part of a d, but it's not. The whole, like b, that's not b. The whole thing is the orbital. Similarly, the little donut here is like part of this d orbital, but that's not a d orbital. It has to be the whole thing. All right, so you should keep that in mind. But d here looks like this guy, doesn't it? Right? So yes. And which one is a p orbital? It's d. Okay? So that's important. These are not parts of orbitals, don't count as an orbital. All right? Okay, it has to be the whole thing. All right. So knowing the subshells of an electron shell, well, it's pretty simple, right? The first shell is just the 1s. The second shell is the 2s and the 2p. The third shell is the 3s, 3p, and the 3d. And the fourth shell is the, you guessed it, 4s, 4p, 4d, and 4f. And, if I went to the 5th and the 6th, it would be the 5s, the 5p, the 5d, the 5f. So the third shell in here is going to be 3s, 3p, 3d, which is separated by commas. And then the first shell is simply 1s. So that's pretty straightforward. Okay, So we've learned a little bit about the Schrodinger model, and we've expanded from just having that one number, the principal energy level, to describe where the electron is, to having four of them describing where the electron is. Three of them describe the region of space, the shell, the subshell, and the orbital, where the electron will be found. And then the fourth parameter describes how the electron is behaving within the orbital. We call that the spin. Okay, relatively complex. Take your time with it. The problems are not that difficult. You just got to have your materials organized. You can do it. If you're having difficulty with it, please don't be afraid to reach out to me.